Hello, welcome to the AP Statistics notes on Chapter 13, which is probability. We're going to be talking about sample space and different kinds of probability, the law of large numbers, mutually exclusive, independence. We'll look at Venn diagrams and tree diagrams. So kind of a lot of little stuff in there, but it's a good unit. I think this is the start of the unit of probability. So there's some basic things we got to just quickly talk about. Hopefully you've read about in the textbook. But yeah, let's get to it. So I think, basic probability, everybody has the idea that, probability can go from 0 to 1, or in other words, 0 to 100%. Can't have more than 100% chance of something happening, or you can't have less than 0% chance of something happening. So that's pretty obvious. That's why when we work with a normal curve or any other kind of density graph, we're always talking about the area underneath the curve is always 1, right? Because it represents 100% of all the different things that could possibly happen. So we have different events that we're going to be looking at. Let me this is so disjoint and independence, kind of the first thing we like to get in our minds all the time, because we're going to start talking about, well, are things dependent of each other or are they independent? Do the probabilities stay the same no matter what you're doing, or do they change? If I have a hat that has 10 different things in it, and I'm going to have someone draw one of those 10 things out of the hat, and then they keep it and they don't replace it into the hat, then all of a sudden the probability for the next draw has changed, because you only have 9 things in the hat now instead of 10. So instead of a 1 out of 10 chance for everything, now it becomes a 1 out of 9 chance for everything. So in that case, the next draw would be dependent of whatever you drew on the first one. But if I replace that thing back in the hat and mix them back up again, now my probability has been reset, and I'm back to 1 out of 10 again instead of 1 out of 9. So that's what we're going to talk about, independent and dependent, and make sure we kind of keep those separate in our mind when we're doing our probabilities, because you have to work with things a little bit different if you have a dependent situation. Another example might be not everything that you draw out of a population is going to change the probabilities. And usually that's because the population is so big. So now let's imagine a really, really, really big hat where I've got 10 million things in the hat, right? 10 million. And I draw one thing out, but I keep it out. Now, technically speaking, because I kept that one thing out, I'm not drawing 1 out of 10 million out. I'm taking 1 out of 9,999,999. So yeah, technically my probability has changed, but it's such a small difference compared to the 10 million that we can ignore it. So yeah, even though some situations might technically be dependent, we're going to treat them as independent, just because we assume the population is so big, it's not going to matter. If I had a big, huge container of Skittles or M&Ms or something, and I draw one M&M out or one Skittle out, it's like the colors are still pretty much mixed the same way they were before. Just because I took one out isn't going to make a difference. Even if I take 10 or 20 out, as long as that vat is big enough, then my probabilities aren't going to change. And that's what we're talking about with independence, right? So that would be independent. Each draw is independent of each other. So when we have large populations and we're drawing samples from those large populations, usually we just consider those to be independent draws. We're not worried about just the 1 out of the million affecting the probabilities. Okay, so independence, really you're talking about, does the probability change or not? If the probability doesn't change from one draw to the next, or from one sample to the next, then we're going to call those independent. Disjoint is this is talking about different outcomes. So if you have two things happening, can they happen at the same time, or is it just impossible? Like, I can't go to wrestling practice and go to tennis practice at the same time, right? Those are disjoint events. I can't do both at the same time after school. So we call them disjoint. You can't do both, right? So we call that, another word for it is mutually exclusive. You hear that? Just maybe disjoint maybe sticks in your brain a little more, but yeah, mutually exclusive. You'll hear people on the news and in other places talk about mutually exclusive all the time. They'll be like, oh, those are mutually exclusive events, you can't overlap them. They're not going to happen at the same time. Okay. So as we get into it, keep those in mind. Yeah, I thought I'd actually show you quickly what those two kind of look like as a Venn diagram and a tree diagram. Um, yeah, mostly tree diagram, maybe, but let's take a quick look. So disjoint with a Venn diagram would be something like you have A, right? A is I go to wrestling practice. B is I go to tennis practice after school, and I leave it so they don't overlap because there's no way you can do both at once. So there's no overlap. I can't do both, right? So there's no probability. If someone asks you, what's the probability you go to wrestling and you go to tennis? I would say, well, that just doesn't even make any sense because you can't do both. It's not even really zero. I mean, it is zero, but technically speaking, you're like, well, they're mutually exclusive. So there is really no probability there. It's just impossible, right? Now, if they're overlapping, now you're talking about events that are not disjoint, right? That are not mutually exclusive, where you can have an overlap. Do you have a science test and a math test on one particular day? Yeah, that can happen, right? A is I have a math test. B is I have a science test. So the overlap is the probability that you have a math test and a science test on the same day. Yeah, that can happen. There is a probability for that to happen. On a tree diagram, let me just draw out. Like there's a chance that A is going to happen or A is not going to happen. Whoops, I didn't want to do that. And A is not going to happen. I'm just going to put this little C. They call that the complement. So if this is the probability of A happening, then this is the probability of the A complement happening, meaning it's not going to happen. So I have a math test. I don't have a math test. And then we'll have B happening. So if A happens, this would be the probability of B happening and B not happening. And even if I don't have a math test, there's still a chance I still have a science test or don't have a science test, right? So we got math tests, no math tests, science tests, no science tests for either case, right? So this is like what it looks like on a tree diagram, which when I really was studying this kind of stuff, I really felt like a tree diagram really helped me understand what my probabilities were for different situations, not only just some basic stuff, for other things too that we're going to get into that are more complicated. So kind of always have a tree diagram in your back pocket. Keep in mind this is only binomial though. Either it happens or it doesn't happen, happens, doesn't happen. Then yeah, you can deal with it. But what I wanted to point out was, let's say there's a 70% chance. Well, I don't know. I'm just like, a test is coming up, but your teacher hasn't told you. I don't know. I'm making up some weird situation, but let's just say there was a 70% chance you're going to have a math test on Friday, right? 30% chance you don't. I don't know why it would be like that. In reality, you always know when your tests are coming up. But anyway, just go with me on it if you will. So let's just say that happens. Now, let's say normally there was a 50% chance of B happening. In this case, maybe having a science exam or something. Now, the question you have to ask yourself is, what are the chances, or do the chances of you having your science test, do they change because you had your math test or because you didn't have your math test? So the question is like, let's say if you have a math test, that you're less likely to have your science test because you're going to go complain and you're going to say, oh, I don't want my science test on Friday. I'm going to have it on Monday or something. So the chance of you having to do that science test is going to be lower, right? And let's say if you don't take a math test or there is no math test on that day, then the probability of you doing a science test has increased to 80%. So there's a 20% chance you won't take a science test if you don't have a math test. But if you do have a math test, then there's a 50% chance of having a science test because you're going to, say, hey, I need to take it some other day, or maybe the science teacher is going to change the date because they know there's a math test going on or something, right? So this, you can see how the probabilities of B have changed because of what happened. So if you have a math test, that probability of having a science test is different than if you didn't have that math test in the first place. That probability changed. So what you're seeing here with the 0.5 and the 0.8 is a dependent situation. The probability of you having a science test is different or depends on whether you're having a math test or not. So this is a dependent situation, and this is what it would look like. This is how you can recognize it. Like if you're drawing it out and you're like, okay, I need to figure out whether this is dependent or independent. This is how you would know. If these probabilities are different, it's dependent. If it's independent, then yeah, these probabilities need to be the same. This has to be exactly the same as whatever it was if you have a math test. In other words, it doesn't matter if you have a math test or not. The probability of you having your science test stays the same no matter what. That's independent, right? One doesn't affect each other. The probabilities don't change from one to the other, right? And I wrote the math test first. I could have done the science test first. Would have been the same situation, right? But kind of a little different context. You would have been talking about, well, whether does the math test probability change depending on whether you had a science test or not, right? You would have switched it around a little bit. But I really like this picture. I really like tree diagrams in this unit because a lot of stuff we do is binomial. Yes or no, it happened, it didn't happen, kind of situations, right? So keep that in mind and you use that to your advantage. And it's going to work for a lot of different situations. All right, let me erase all this. We'll keep moving, see what we got. Some of this is just notation wise. Like I said, probabilities are 0 to 1. We need to get used to start using the P with the parentheses for the probability of something, right? Probability of A. We've used it a little bit already, so hopefully you're used to that by now. We talk about sample spaces representing everything. This is just old stuff. The complement rule we need to look at real quick because it can be useful. You can really use this to your advantage. The whole idea is that sometimes it's hard to figure out what whatever you're having here could be something complicated. And so just trying to do, let me do it this way. Like the probability of A is real. It's written over here. Sorry. So the probability of A, for some reason, is complicated to figure out. Like there's a bunch of pieces to it or something. It's really difficult to figure out. But the complement of it, the probability of it not happening, is a lot easier for some reason. And I'll show you an example in a little bit here. So if that's the case, it's going to be easier to do the probability of it not happening and then just subtract that from 1 because, of course, we know there's 100% total. So, if A was 70%, then the complement would be 30, but you could figure out that 70% from the 30, of course. So like I said, maybe this is just easier to figure out for some reason than the other one is. And I'll show you what I'm talking about in a minute. Okay, so addition rule. And multiplication rule is next, right? So first is addition rule. So what can we do with probabilities? Well, if something is mutually exclusive like this, and you want to find out like what the probability of A or B happening is. So in other words, we're going to use, you'll see some notation later, but in other words, like what's the probability that I go to wrestling or tennis? You don't have to do both, just you're going to be in wrestling or you're going to be playing tennis. Those, if it's either or, then that means both probabilities add together, and that's why they call this the addition rule. So, if there's a 20% chance I wrestle and there's a 50% chance I play tennis, then there's a 70% chance I do one or the other. Now, of course, it's not both, it's just one or the other. But I can say, yeah, it's kind of like saying there's a 70% chance I'm going to play a sport, right? Period. There's a 30% chance I won't, but I'm only interested in wrestling and tennis or something, right? Now, I know maybe those are bad examples because they're different seasons, but you get the idea, I hope. Okay, so maybe I should do wrestling and basketball, right? Because you can't do both. Okay, anyway, I hope you get the idea. You can just add those together. Just add them together. It gets a little more complicated. So I said like 20% chance of wrestling. I'll switch it to basketball. 50% chance I try out for basketball. So there's a 70% chance that I play sports. Now, if it was something like this is where you can do something together, right? Oh, there's a there's a 40, well, let me get rid of that. There's a 40% chance I go for a run today. There's a 30% chance that I watch TV tonight instead of reading a book or something, right? But those are not mutually exclusive. Those can happen at the same time. I can go for a run today and then come home after my run and watch TV. That's totally possible. So there's this overlap. So if I was going to talk about the probability of A or B, right? A or B, we're using the word or now. That's for this whole addition rule that we're talking about. This one, I just add them together. 0.2 plus 0.5, just add them together. I got nothing to worry about. But here, let's say there was a probability that like 10% chance I've figured it out somehow. There's a 10% chance I'm actually going to do both, right? So the 0.4 represents this whole outer circle, all of it. The 0.3 represents all of that circle, all of it. So if I just say what's the probability I go for a run and I watch TV, and I just try to add these together, that's going to equal 70%, which is going to actually be too much. It's not 70% because 10% is overlap. So I actually have to subtract 10% to get the real probability, which is 60%. So when someone says, oh, what's the probability you're going to run or you're going to watch TV? When they say or, that includes both. I could be like, I go run or I watch TV or I do both. So the real probability is only 60%. It's not 70. Very strange maybe, but you got to think about this. There's a 30% chance that I run and don't watch TV. There's a 20% chance I watch TV, but I don't run. And then there's a 10% chance I'm doing both, right? So altogether, that's just 60%, not 70, because the 10% was shared in both circles. So keep that in mind. That's the general rule of the general addition rule, which is kind of more formally introduced later, but I always like to talk about it right now because you can't just think the addition works in all cases. It only works for mutually exclusive. The general rule where you have to subtract the intersection, that works in all cases. Just erasing and we'll move on. Look at the multiplication rule. Okay, so so this is your addition rule, multiplication rule. So multiplication rule, this is talking about instead of the word or, now I'm going to have the word and. And when we had or before, that means they're happening at the same time, which means that when you have your probabilities, maybe A and B or something like that, when I use the word or, I'm going to use this notation, this upside down U, right? That's not the intersection, but the union, not the union, sorry, the intersection, yeah. So the intersection of these. So this, oh, I'm sorry, this is wrong. It should be union. Oh. All right. So or means union, right? You're just adding them together. That's the addition rule. Now we're talking about and. So when you do and, now you're using the intersection rule, like the intersection symbol, the upside down U, where this is where things are happening at the same time, right? So when are A and B happening together? A and B. So we're going to multiply those probabilities, okay? Multiplying. So what does that look like? So multiplication rule doesn't work if you have mutually exclusive events. Just wouldn't make any sense. So if I have two things that don't overlap at all, there is no intersection. So what's the probability of A and B? Well, nothing, zero. It doesn't happen. They're mutually exclusive. It doesn't make any sense. But what if they are overlapped and they're not mutually exclusive? They can happen at the same time. Well, then, yeah, you're going to multiply those probabilities together. So in this case, 0.7% chance that I'm going to eat a peanut butter and jelly sandwich, 0.5% chance that I'm going to drink a Coke. So the probability of me eating a peanut butter and jelly sandwich and having a Coke at the same time, you would multiply those together. and get your 0.35, right? 35% chance that both of those happen at the same time. Not too difficult, but you got to really know your rules, because when it does get difficult, you need to know what to do and when to do it. Because it starts to get a little jumbled around with disjoint, not disjoint, independent, not independent. Are they, are you doing or? Are you doing and? And so it starts to get a little jumbled around. Okay, so you can see the symbols there on your notes, and which we already talked about. Okay, so let's do an example. So they take a survey for M&Ms, and they ask Japanese people, if we were going to introduce one new color to the M&Ms bag, what color would you add? So we got 38% pink, 36% teal, and 16% purple. If you're like me, and the first thing I always do is I add these up, and I'm like, okay, is this all 100%? 30, 60, 70, 84, that's 90%. So that means there's 10% missing that I don't know what happened. Maybe it's some other color that people were choosing, or maybe they just didn't choose to answer, or I don't know. Okay, so there is 10% missing here. I just always keep that in mind. Okay, so what's the probability that they preferred pink or teal? So the word or should tip you off that it's addition, pink or teal. So you just add those together, that's 74%. And I'm not writing it out nicely like I really would on a free response question. I'd be using probability of pink and the or I could use this or teal, or you can just write the word or, like if you're watching me go, man, I'm going to mess up the upside down U and the blah blah blah, well then don't write it, just write the word or. You can just say pink or teal and just put it in a probability and get your 0.74, and you'd be good to go. You don't have to use the little symbolic notation if you don't want to. Okay, but we do need to kind of write those out properly, so get used to that for free response. If we pick two of the I think this is supposed to be two, TWO2 respondents around, what's the probability that they both selected purple? So now we have two people selecting purple. Purple 16%, and we don't have one, we have two now. So probability of the first person picking purple is 16%. Now two things are happening at the same time, right? Two independent people. They have, like, one doesn't affect the other. We're assuming that just because one person picked purple, the other one can still choose whatever color they want. They don't know what everybody else picked. So their choice of purple is also 16%. It doesn't change. And these are both happening at the same time, so I can multiply, because this is an and situation, right? So when I say both, I mean this first person and the second person. So this is multiplication, and you have to multiply those guys together. And I think, what do we get? We get 0.0256. So 16% chance of one person picking purple, but for two people, that becomes a lot less, right? That's all the way down now to 2%, 2.6%, yeah? So if we pick three respondents at random, what's the probability at least one preferred purple? Okay, so this is purple, 16%, but they say at least one. Let me erase this stuff because I want to write this out for you. So we're picking three people, 16% purple. So I'm going to use this 16% here. And it's kind of you have to think about all the possibilities. As soon as you start getting combinations of things, we have to start using the binomial theorem. If you guys remember Pascal's triangle, maybe from Algebra 2, and you did like 1, 2, 2, 1, and 1, 3, 3, 1, etc., right? And that was for when you had a binomial, a plus b, and you expanded it using n, right? So maybe it was a plus b to the 0 power would be this one up here. There'd just be 1. A plus b to the first power would be 1a and 1b. If you go to second power, then you'd be going 1a. You'd get 2a times a plus b times a plus b, right? So if this was second power, you'd be looking at this, right? A plus b times a plus b. And I know right now you're like, where is he going with all this? But if I were to distribute that out, I'd have a squared, I'd have one of those. I'd have a times b and another a times b, that would be two of those. And then I'd have b times b, and I'd have one of those. If this went to a third power, if n was 3, and I added another one onto there and distributed it all out, right? I'd have 1a cubed, but I'd have 3 that had a squared and a b. I'd have 3 that was a b squared, and I'd have 1 b cubed, right? So the 1, 3, 3, 1 comes into play there. Why am I doing this? Well, in this case, we said we had 3 people, right? We were going to pick 3 people, and they have a choice of being, and the options are either they chose pink or they didn't choose pink. So the probability of choosing pink is 0.16. The probability of pink is 0.16. The probability of not pink complement, is 0.84. But that's for each individual person. So you have to think, well, there's different options. I could have had the first person choose pink, and second pink, third pink. I could have had first pink, second pink, and the third not pink. Or maybe it was the second person who said not pink. Or maybe it was the first person who said not pink, and the other 2 did say pink. Or maybe it was 2 people who said not pink, like the first and the second person, right? And you're getting all these options, and you're like, oh my goodness. It could have been the first and last person who said not pink. It could have been the second and the third person who said not pink. Or they could have all said not pink. If I ask 3 people, right, these are all the options. So this first option represents the 1 on my Pascal's triangle. And then these cases all represent where 2 people picked pink, but the third person did not. So 1 person did not say pink, but 2 people did. So you can see how there's 3 ways that could have happened. So this is just like combinations and permutations. These are combinations, right? So there are 3 combinations of 2 people not choosing pink, but 1 person choosing pink. So there are 3 of those combinations, right? And then there's only 1 way where all 3 people did not choose pink. That's a lot of work, so I'm showing this for a reason. I'm showing you, like, well, 1, it's kind of a glimpse into how you should be thinking, but 2, you should be thinking about, is there an easier way to do this? And there is. So the way they said, what's the probability that at least 1 person chooses pink? So that would have been this case where all 3, this case where 2, and this case with 3. I'd have to do all those probabilities and add them all up. But you'll notice there's only 1 case where none of them chose pink. So wouldn't it be easier if I just did 1 minus the probability that all 3, right? The probability of all 3. So I'm going to do 1 minus the 0.84 cubed to get my answer. So this little instance at the bottom is the 0.84 cubed. If I take 1 minus that, I'm going to get the probability of, like, all of this together, right? All of this together would be 1 minus. This is just a 0.84 piece, right, cubed. So it's much easier to do this probability than it is to do every single one of these, or, try to figure out all these together and do them all up and add them all together and get all those probabilities together. You don't have to do that. Just find the easiest one and subtract from 1. So this is that complement situation. But it's a good look at what you're doing. So when we start doing more than like kind of combinations of things, you do actually have to worry about the combinations. And that comes from Pascal's triangle and factorials and all that kind of stuff, right? So we'll look at that more later. But right now, we want you to just use the complement rule. Do the easy thing and then subtract from 1. It's going to be easier. All right, that was a lot of writing. I got to erase. Here we go. I wish I had just a erase all button, but I don't. I need a better tool. All right, so hopefully that's coming together a little bit. In the beginning, they're not this difficult. Well, they are this difficult, but you don't have to write it all out like I did, right? You should just be using the complement rule at this point, right? All right, last one. What's the probability 3 respondents in a row pick pink? Well, that was kind of, if we would have thought about that earlier, that might have helped us with the last problem a little bit, but all pink. Well, I think I was doing purple before because I used 0.16. Oh, they said purple on part 3. Never mind, so I was all right. Okay, so 3 pinks. Well, this is easy. I don't have to worry about all that combination stuff because they're just all pink. It doesn't matter the order necessarily or anything like that. I'm just going to go 0.38 times 0.38 times 0.38. It's the multiplication rule. They are all happening at the same time. So if you go 0.38 cubed, you'll get 0.0549. So 0.055 basically. And that's good enough, okay? We got some dice problems. I'm not going to go completely into there. Just make sure you can practice kind of just counting things up. The probability of getting a 6. Okay, you just add all your 6s up. Here's a 6. That's 1, 2, 3, 4, 5. So that's 5 different ways you can get a 6 out of the 36 different combinations, right? So that's 5 out of 36 different combinations, and I have my probability. So just make sure you can do those kind of things, right? Counting things up. What they're getting at here is that when you see an or, you add them together, right? You add the totals up, how many you have, right? You can have a 5 or 9, so you add them up. And then down here, you can see it's a 7 and not a 7. So when you say and, you're kind of multiplying things, right? So you can see we're doing 2 rolls. So the first roll, you get a 7, but then the second roll, you don't get a 7. So what's the probability of that kind of combination together? So you're going to multiply those probabilities because it's an and situation. All right, so there's disjoint and independent again. We already talked about. Last thing I need to talk about is law of large numbers. There's a weird thing going on in the world, like in the universe, if you will. And it's kind of, I don't want to get too philosophical on you. I like space and I like time travel and I like all these kind of probability things. Is it possible to go forward in time or back in time, or quantum mechanics and quantum tunneling and all these kind of things that seem to only work on probabilities and they don't really have a location or things like this. So there's this thing called law of large numbers, which for us, all you need to really know is for each individual trial of something or each individual person or thing or whatever it is you're doing, for each individual thing, they are usually they're independent. But even though you have independence for each individual trial or each individual draw or each individual thing that you're looking at or that you're measuring, even though each individual one is independent, over the long run, if you do a combination of them, you have probabilities that the totals tend to come close to. So you can see this first graph. This is about like, did you get a green light or a yellow light or a red light? When you came up to, like here, you see it says like % green lights. So when you're driving down the road, do you get a green light or do you have to stop at the light? So they had 5 different cars doing it. So you can see for car 5 in the yellow here, it was like they were like no green lights. They hit every single red light along the way, really bad luck. And then they started getting more and more green lights over time, right? And then for the blue one, the car one, the blue car, it hit like right in the beginning was hitting every green light, and then it hit some red lights, and then some more green, and then so the percentage started to kind of level off at a certain percentage. And you can see this is the long run of the same situation. So this graph is just kind of cut right in here, this little piece, right? So, but over the long run, it seems to level off. Doesn't matter how you started. Like in the beginning, everybody had a different experience. But over the long run, the percentages kind of leveled off to like 35%, maybe it looks like. So in general, over the long run, on average, right? No matter what, no matter who you are, what car you're driving, or what your path is that you're taking, probably, you're going to hit green light about 35% of the time, and you're going to hit red lights like 65% of the time, right? In general. Now, does that mean like if you got a whole bunch of, let's say I get a whole bunch of green light, green light, green light, green light, green light, does that mean that the next one has a higher chance of being red? And the answer to that has got to be a big no. And you got to be really careful of that. This is a trap that everybody falls into, gamblers and stuff included, and myself. It feels like if you get a whole bunch of greens in a row, that you're kind of due to get a red. But that's not true. It's not true. The next one has the exact same probability as it always did of being green. I always tell the story. I went to Atlantic City, right? And I like to play roulette. And in roulette, you can play black or red, right? Now it does have this, it has 2 spots for green, but it has, I think it has what, 36, 36 numbers that are either black or red numbers, right? 18 red, 18 black. And then they have 2 numbers that are green, but just ignore that for the moment. But so I was playing black and red, and I started playing red, and it didn't hit. It went black and black and black, and I just kept betting red, and to get my money back, I started doubling up. I was like, okay, I lost the first one, so instead of betting $1, I bet $2 on the next one, trying to make my money back. And then it hit black again, even though I was betting on red. So I lost the first dollar, plus I lost the $2 on the second bet. So I lost 3 total so far. So on the next bet, I would bet $3 because I wanted to make my money back, right? So I'm betting 3 now. And then it hit black again. And so I lost 1, I lost 2, I lost 3. So now I lost $6. So it keeps doubling. So on the next bet, I bet 6, and then I bet 12, and then I bet $24, and it just keeps adding up. And it kept hitting black and black and black. And I'm like, eventually it's going to hit red, right? I mean, it has to. But that was my mistake. It doesn't have to. It could go black forever, and we would, like, there's nothing in the world that says it, like the very next spin of the wheel, and they put the ball on the wheel and stuff. There's nothing saying that it has to hit red. Nothing says that. You're not owed anything, and there's nothing telling you that next roll will be red. Nothing. But the weird part, and this is where it gets philosophical maybe, where you get quantum tunneling and you get kind of weird probabilities going on. We could talk about it. Please talk to me about it if you're interested in this kind of stuff. But over the long run, there is an actual something in the universe saying that, yeah, over the long run, if you keep going, now notice these are really big numbers. If you get really, really big numbers relative to your probabilities, then yeah, you will get some blacks and you will get some reds. So it's not that for each individual roll of the dice or toss of the little ball or whatever, for each individual one, anything can happen, right? Anything can happen. But over the long run, the probabilities will equal out to some number over the long run, right? On average. So averages have some kind of law about them, averages. But individual independent events do not. So don't fall into that trap. Don't be a gambler, because the law of averages are in the favor of the house all the time, right? Now let me get physics on you. So if you want to think about physics, if you're talking about an electron cloud or something, where that electron is at any particular time, you have no idea. It could be anywhere. But over time, it kind of traces off a path in a particular zone, like an energy zone or something. I don't know my physics that well, but it has some kind of energy zone, right, to where it should be. So there is a level somewhere, there's an average somewhere, but for any particular electron at any particular time, you don't know where it's going to be, right? Same kind of idea. Anyway, so talk to me about it if you're interested in that kind of stuff or you want to talk about that more. But to me, that just blows my mind. Like anything can happen, but over the long run, it doesn't, right? Over the long run, it doesn't. That's law of large numbers. All right. That's it for the notes. Let me know if you have any questions.